Okay, welcome to the second part of our last topic on analysis of variance. So this video is going to show you how to compute uh, an F-test in Excel, and also talk about something that you want to do after a significant result in an F-test is to actually determine which groups are really different from the other groups. So if you haven't watched part one, you should probably do that so that you can get some of the background. So we'll dive right into it. If you open up, if you've downloaded the file on Blackboard for in-class ANOVA, and you open it up, you'll find that the first page looks something like this. So you have three columns of data. Each column represents a group, and this is the same data from the other video. We have it right here. And so anytime you want to run what we call a one-factor ANOVA, which means there's only one thing that makes groups different from each other, as we have here, you're going to want to enter the data in each group in a separate column and give a descriptive title. And each cell represents a single person. In this case, we're measuring the amount of corticosterone level in the blood at 3 points in a semester. And each group has different people in it. So if you were in the study, you would only be measured once. So this is what we call a between groups design. So the first thing that you want to do, and again, you're going to need the data analysis pack in Excel, is go ahead, so we'll switch over here. Go ahead and click Data, Data Analysis, and scroll all the way to the top and you see ANOVA single factor. That's the one that you want to select, and you select OK. I lost my data here. And so this is actually quite easy. The input range, like for the t-test, you had to select each column separately. For a single factor ANOVA, all you have to do, the default is that the data are grouped by columns as they are. So you press the little square, and including the labels, go ahead and select all of the data as I just did there, and press enter. Now, very importantly, you need to tell Excel that the first row of the selection contains the labels. We're going to do our test at alpha 0.05. And again, I like to select an output range in my sheet. So I'm just going to go ahead and select a blank cell here over in column F and press enter. And that's it. So input range, you go ahead and select everything you've got, including the labels. Leave that, that's the default. You do have to click the labels box, and alpha's in there already. You could change it if you want to, but just leave it where it is. And then again, I like to select an output range, and I'm going to press OK. All right, so let's take a look at my output. So the output that we have, and by the way, if you're following along in the slides, we're now here. We've done all of this, and we've got our output. Right? So this is annotated for you. And this is the same output that you saw in the other presentation, including that p-value that was in exponential notation. So notice that it says 8.5386 e negative 5, right? And I've got that cell selected. So select that cell. You look up here, this is the actual number, 0.000085, right? So that's a very small number, right? And importantly, if we were using alpha 0.05 as our criterion, then this number is much lower than that. So this is the bulk of our ANOVA. The critical value you can ignore. That's something you can do if in addition to using the p-value, but we're not using that method. So the important things down here are, if we make column A a little bit larger, we can see we've got our between groups and within groups source of variation, sums of squares for each one, degrees of freedom for each one, mean squares, and then a single F value that represents our test, right? So this is a large F, 22.59. this p-value is very small, which means that there is a significant effect of the time in the semester when corticosteroid was measured and the level. And what we see up here is we actually see for each group the average level of corticosteroid. And we can see 3 very different numbers. And this result tells us that this is a significant amount of variation amongst the groups relative to the variance within the groups, meaning that the time of the year that you are tested is likely systematically affecting the corticosteroid levels, or more specifically, that we can reject the null hypothesis that the time in the year has no effect on the measured level. Right? So this gives you an overview. Slide number 6 in this in the part 2 lecture. It just gives you an overview of the values. So let's then the last part is to do effect size. So this was the calculations I gave you on the last slide, but let's take a look at it in Excel. So omega squared is our measure of effect size, and what we need to do is we need to form this ratio. And so the way we're going to do that is, and if you downloaded the data, you'll see that all this is done for you, but you want to go ahead and do it yourself. So where it says omega squared, what I'm doing is I'm going to form the numerator. So sum of squares between 203.33 minus, now I want to protect this with parentheses. So parentheses, I want to do k minus 1, which I can type in, or I can recognize that that is actually the degrees of freedom between groups, so 2. And then I want to multiply that by the mean squares within, which I find right here. And now I want parenthesis there, and now I want another parentheses to protect the numerator. So that's the numerator. Then we're going to press the slash for divide, and we're going to form the denominator, right? Which is, again, we need another parenthesis. We're going to take the sum of squares total, 257.3333, and plus add that to 4.5 again. Okay? When we close our parentheses, and again, when you're dividing in Excel and you have to do operations in each of the thing, you want to protect the whole thing with parentheses. So if I press enter, I get at 0.742. If you want to see this out, right, what I've done, right, if we do just the numerator, is I've done equals 203.333 minus 2 times 4.5. That's our numerator, right, 194.33. And the denominator, sum of squares total, right, this is equals 257.3333 plus mean squares within, which again is 4.5 from our table. And we get that. And if I was to divide those two together, so I take the numerator, divide, right, I get that same result. And a little bit off because I didn't, by doing what I did here, which is just selecting the cells, I eliminate that rounding error that I've got there. Okay? So the key to forming formulas like this in Excel is to just really watch out for parentheses and make sure you're putting the parentheses in where they need to be. Okay. All right. So again, effect size is a function of a bunch of stuff that we have in our ANOVA summary table, and that's the reason that it's output. It's the reason that Excel gives you more than just the F value and the P value, because these values are very important. Obviously, they're the values that lead us to compute the F value, but we can use them for various effect size calculations, and this is one of them. So as I said in the last chapter, we want to write this up, or last lecture, we want to write this up in the following way. We want to say that we've done an analysis of variance, and we want to identify what our independent variable was. It's external stress. We want to end up write what our dependent variable was. Right? So an ANOVA was run with external stress as the independent variable and corticosternal level as the dependent variable. And then we say what we found. There was a significant effect of external stress on corticosterone. Why can we say significant? Well, assuming that alpha was 0.01, it could have been even smaller. We found that our p-value was 0.000853 and change. Now notice what I did is, because that's so low, I can simply write that p was less than 0.001, demonstrating that an alpha as low as 0.001, still we would have rejected the null hypothesis. To be safe, you can write it this way. Either way is fine. And then we put omega squared there at the end. So little omega looks like a little w, squared is 0.74. Okay? So that is how we write up the inferential component, or one part of it. And then what we want to do is, all you've done here, this is very important, when you do an analysis of variance and you have more than two groups in your design, the result, and especially if you get a significant result, is only telling you that the groups are different somehow, that there is significant variation amongst the group means. It does not, however, tell you, what if you had a specific question about which two groups were really very different, right? Because that can happen. It could be that just one group is driving the effect. It could be, for example, that stress levels measured right after vacation and a week after vacation are quite similar, and that what's really driving our effect is that stress levels spike way up at final exam time. So the results of an analysis of variance with, like we see here, will not give you that information directly. What it does is, if you have a significant effect, it gives you sort of the green light to then try to investigate, well, which of the groups, which of the pairs of groups are really, really different. And so to do that, we have to perform what are called post-hoc tests. Post-hoc just sort of means after the fact. So this means after we've run an ANOVA, we need to do a little bit more of a fine-grained analysis. Like I said, though we found a significant effect, our ANOVA only indicates whether all the means are equal, or basically, if we reject the null hypothesis, it's sufficient just for one of the groups to be real different from the other two, but not necessarily that all three groups would, say, be significantly different in pairs, pairwise, using a t-test, right? So to make decisions about that, if we were interested, and we usually are, we do what are called post-hoc tests or post-hoc comparisons. They're essentially variations on t-tests and f-tests, but with two groups. And then they're adjusted such that the decision rule, so our decision as to whether we have a significant difference, is adjusted so that we don't inflate our type 1 error rate. Because we've already made one decision in the study which could have a type 1 error. If we rejected the null hypothesis, there's a possibility we've made a type 1 error. If we then continue to do tests, the type 1 error is additive. So if we do 3 more tests, each at 0.05, we're going to be up to quite a bit of a chance of a type 1 error across those tests. So post-hoc tests simply just adjust the t-test or f-test procedure for two groups so that we avoid that situation. Now, if you look at various statistical packages that run this online, Excel does not. We're going to have to do it by hand, but we can use information that we have in the table. There's about 20 different procedures that people have proposed to do this. There's actually more than that. We're going to choose just one. It's a very simple one. It happens to be one I think that's actually a little bit liberal, meaning that some people think it's a little too easy to reject the null hypothesis, but it's a good illustration of what post-hoc testing is all about. So it's called Tukey's, and that's Tukey, not Turkey, John Tukey, very important statistician. It's called Tukey's honestly significant difference test. And it's a procedure where, again, we just are adjusting the alpha level when we test two groups amongst each other. It's a simple adjustment of the T formula. What happens is we're not going to use the p-value method. So we're going to use a critical value method. So what that means is instead of getting a p-value for this test, we're going to get a test statistic, and we're going to call that test statistic Q obtained. Then we're going to look in the book on page 609, and I will show you that. Okay. Page 609 in the book has what's called the studentized range distribution. So this is a probability distribution. Okay, go away. Oh boy. And what we want to do is we want to pick our alpha level, and based on some parameters of our design. So the first parameter is what number of groups do we have in our design total, and it's 3. So we're going to pick a number from this column, and then it's asking us, well, what's the mean squares within degrees of freedom? So if we look at our output in Excel, the degrees of freedom for the within groups line is 12. So we use 12 as our other parameter, and we find two values that we can use. Excuse me, this is the column, 3, right? 3 means and 12 degrees of freedom within. So it lists 3.77 and 5.05. Over here, this is basically saying that if you would like to test if you would like to use a test in which across all the tests you do, you're keeping alpha at 0.05, you would use 3.77 as your critical value. If instead you'd like 0.01, you can use 5.05. So that means we're going to use 3.77 as our critical value. Okay. So what does that mean? The first thing that we want to do is we want to, for each group in our design, or really each pair of groups. So there are, whenever we have 3 groups in an experiment, there are then 3 unique pairs of groups that we need to test for differences. So in this case, it's vacation group, which is group 1, first week of class, which is group 2. So that's 1 versus 2. Then group 1 versus group 3, and group 2 versus group 3. And so in general, what we need to compute for each of these 3, so we have to do the following thing 3 times. This formula says for any pair of groups, I and J, so let's say group 1 versus group 2. Right? So I is group 1, J is group 2. Take the mean, the sample mean from group I, or group 1, and subtract from it the sample mean from group J. So that's just, the numerator is just saying, take the mean corticosteroid level from the vacation group and subtract from it the first week of class group. So from our data, that's 4 minus 8. And this, right, means take the absolute value so that we have a positive number. Then we're going to divide by this, which is essentially just an adjusted standard error. Right? We take the mean squares within groups, right, from our ANOVA table. And here we divide by little n. So another problem with Tukey's procedure is it only works if both groups have the same number of people in them. And little n is going to be that number. Right? So that's going to be 5. And so we would just do that comparison. We would compute, that leads us to what we call Q obtained, or Q test statistic. So we're going to do that for each of the pairs of groups. Well, let's start with the first group. So here's our Excel output from Excel. And we see that, again, Q obtained, we're going to take the mean of the first group after vacation, which is 4, and subtract from it the mean of the second group and take the absolute value. So that's 4 by 8 is -4, and absolute value is 4. And then the denominator, again, looking at the formula, is the square root of mean squares within divided by n. So from our table, mean squares within is 4.5, n is 5 because there's 5 people in each group, and we get 4.5 divided by 5 is 0.9. We take the square root and divide, right? And we get our Q obtained of 4.21. So let me show you this in Excel. So what we need to do is we need to take the mean of the first group. So we'll do equals mean of the first group, 4. Actually, we'll type ABS for absolute value. Mean of the first group minus mean of the second group. So that's 4 divided by 4 minus 8. And we're going to divide that by the square root of mean squares between groups, 4.5, divided by the number of people in each group, it's 5. And we get our result there, 4.2163, so on and so forth. So we have that from the table, our critical value is 3.77. And so what we have here is we answer the question, is Q obtained greater than Q crit, right? So 4.21 is our Q obtained. Is it greater than Q crit? Yes, it is. And so what does that mean? That means that reject null, groups differ significantly, okay? So the procedure for a Tukey HSD test is to first compute Q obtained, which is a function of the 2 groups that you're comparing their means. And then we make this new standard error term by dividing mean squares within by the number of people in a single group, which is 5. And we get a value called Q obtained. If that value is greater than our Q critical value, which it is, we reject the null hypothesis. If it's not, then we do not reject. So we got our first Q critical value. And since it's larger relative to our Q crit, so first Q obtained, larger than Q crit, it means that the vacation group and the first week group significantly differed with respect to corticosterone levels. So there was a significant difference in corticosterone levels between these 2 groups by themselves. If we look at groups, group 1, vacation group versus group 3, this should also be significant because if you notice, it's the same denominator, right? For all 3 of these tests, the denominator doesn't change. In this case, if we want to compute it on its own, the denominator, which is an adjusted standard error, is equal to square root of 4.5, which is mean squares within, divided by 5, little n. So our adjusted standard error is 0.948. And so since we're dividing by that each time, and we know that when we divide a difference of means of 4 by that number, we get a significant Q value. Here we've got a difference of 9 units of corticosterone level in the blood, and we get a Q critical value of 9.4868. So again, we can compute that as equals this mean, oops, we'll do absolute value, this mean minus this mean, and divide by square root of 4.5 divided by 5. Right? And so yes, so reject null, groups differ significantly. So this is telling us that also you get a significant difference in corticosterone levels when you compare just the vacation group to the finals week group. Our final comparison is then groups 2 versus groups 3, right? Mean of 8 to mean of 13. So we'll do the same thing here. we'll do absolute value of the difference between 8, so 8 minus 13, if you want to just type it in, divided by our standard error term, square root of 4.5 divided by 5. And again, yes, right? We're bigger than Q crit, so we reject null. So notice we're not using a p-value. Right? Instead, what we're doing is we're computing each of these are test statistics. They're similar to t-values. They're a little bit different. And we use a method whereby instead of getting a p-value, which we could get, it's just a different type of distribution. Instead of doing that, we say, to reject the null hypothesis at alpha 0.05, right, we would need, so the critical value says that we would need our Q obtained to be at least 3.77. So any Q obtained that's greater than 3.77 means we can reject the null hypothesis that the groups are the same, and so they must be significantly different. So if we had answered no anywhere here, we would say, oh, that's not a significant difference between the groups. So here we have a situation in which all three groups are significantly different from one another. We have a big effect size, and we have a big F value. That's not always going to happen. Sometimes you get an F value, and your answer, you've only got one group difference. So you've only got two groups that are really different from one another, and then the rest of the groups are kind of similar to one or the other of those. So so it's not always the case that all of your comparisons are going to be different. So there's the math for that third one. And again, all of this, by the way, is broken down in the book on pages 424 to 425. So now we want to compute this, communicate it. Oh, here's again the results of our comparisons. We want to take a look at that. But let's look at now what we would do with this information. So we've already written this part up. Right, so if we were contributing to a poster presentation or an article, we would want to summarize the results of what we've just done. So we did the first part. Then second part, we say, well, what post-hoc test did we do? We did Tukey's HSD, and we have an alpha 0.05 across the tests. Now here's where sort of the art comes in. What I've done is I've just kind of made a statement. Well, all three groups have differed significantly, right? Because all three of our comparisons led to the conclusion that the groups were significantly different in terms of their corticosteroid level. So I just make that statement first, and then I go through each test, right? The first one, I say corticosteroid levels taken after vacation. And note, I'm giving then the sample mean and sample standard deviation for that group, those 5 people. I see that those levels were significantly lower than those taken during the first week of class. That's group 2, and that's their sample mean and sample standard deviation. Then I move to the second comparison that I did. Corticosteroid levels taken after vacation were also significantly lower than those taken during finals week. And then I give the finals week group sample mean and sample standard deviation. Now, why didn't I repeat group 1's information? Well, it's already there. Once you give the sample descriptive statistics, you don't have to relay it. So notice that each group's descriptives appear just once. And then the last sentence just summarizes the third comparison. Corticosteroid levels were significantly lower during the first week of class compared to finals week. Okay? So that's how I would write that up. It's just very straightforward. You go group by group, test by test, say what you concluded, and give the descriptive statistics, sample mean, sample standard deviation. So there's just some tips on doing this. If you were asked to write it out, again, state the procedure for post-hoc test in the alpha level. Introduce each group mean and standard deviation. First time it's mentioned. By the way, you'll notice that the output from Excel only gives you the variance. Right? So there's 2 ways to get standard deviation. You could go back to your data and compute it from the data, or you could simply make a little column here where all right, standard deviation is the square root of the variance. So if I take the square root of this group's variance, I get the standard deviation. If I do it again, get that one. And now I have my standard deviations, and you can check that that matches what you would see here. And again, we use the word significant when the groups pass the test, meaning we reject the null hypothesis. And so again, if a Q value is very low, lower than the critical value, we would say the two groups did not significantly differ. However, we did not find that that was the result of any of our post-hoc tests in this situation. All right. So before the quiz, you might want to try on the second page of your spreadsheet is another experiment, which is in the book, which has to do with the effect of different types of lecture presentation on exam grades for a comprehension test. And I've given you the output, and I've also given you the Q obtained. So go ahead and see if you can reproduce that and try your hand at a write-up. Because some components of that will be on the quiz, just to make sure that that you know how to do that. Okay, so that's it. That actually concludes all of the content for our course. There's much more to statistics than where we stopped, but again, our focus was more on making sure we understood p-values and how that goes into significance testing. Most of the things that we haven't covered are variants of the procedures that we've learned, with some exceptions, and you would learn how to do those in various applied settings if you needed to. So go ahead and try it, and hopefully we should have minimal problems, and that's that.